And so I think we are in start from 9.3. That is what we, after you substitute retarded condition and then using the single frequency mode. So everything proportion to the eta minus I. So like A xt is, you have the spatial part multiplied by this exponential time dependency. And obviously this thing, this like a Fourier component, so A can be a compact value now. Anyway, with this kind of notation, just consider the spatial part is given by 9.3. Let's see, over 4 pi integrating to x pi, and then divided by x minus x pi, and then you have this exponential function. Right, and this k is just the wave number, and we are also considering vacuum, so we're not considering it in a medium yet, but, because that is, depends on the medium. Can be very complicated. Omega is C over omega. K is C over omega. Omega over C, right? No, CK over omega. CK over omega. So C, right? Yeah, omega over C. Right. So that's the wave number. And now the long wavelength approximation. Yeah, we can. I mean, actually, it's, does it have to be long wavelength, or you can use just the fact that you're outside the source, and then but basically the source J is some localized current density, and you consider observing in actually X, which is outside the source, basically X. X is much greater than X prime, where X prime is where J is non-zero. Outside a certain X prime, I mean, obviously center your origin at somewhere within the region where J is non-zero. So all this X prime, when J is non-zero, is smaller than X. Then you can do a Taylor expansion of X minus X prime. So well, it's Taylor expansion or binomial expansion, whatever you want. So we did that before. You know, it's just the square root of x minus x prime square, and then square root. The reason to do that is you can do this square easy, square. I think it's just use R. Yeah, x, so x, the magnitude of x is called R. Just the radial coordinates R squared minus 2 R. I mean, to x dot x prime. Let's keep it x dot x prime first, and then plus R prime squared, and then 1/2, right? And obviously, when R is greater than R prime or x prime or R prime, then this is a linear term. This is second order term. Be the this term, and then the rest is just binomial expansion. This is R 1 minus. So divided R squared to be the second term, and then use the binomial expansion, keep the linear term, you have 1/2 times minus 2 x dot x prime divided by R squared. Right, and the 1/2 cancel with this, x minus x dot x prime is R squared, approximately. Or, I mean, that's no, this is actually this. We define this as R minus. We define that as a univector R. I mean, you can use R hat, but then Jackson actually use N. I mean, it doesn't matter for Jackson's notations. N is just, so this is R times N. And dot x prime. Okay, so this is 9.7, right? The reason to do that is you can substitute this into that, right? And now consider the far sum or the radiation sum far sum. And far sum is x is really larger than the wavelength, and so x r greater than lambda. It's always long wavelength, but r is also much great number. And in this case, the denominator, you can always ignore this x prime term. Okay, and so a x will be, now you have this into here, that exponential function separate in two factor. You can pull out one of the factor, e to the I, right? This into here. So part of the exponential becomes either IKR, because R doesn't involve in the integration. Pull that out of the integration. And then 4 pi. And the denominator becomes just all, because it just ignore x pi in the denominator. And then so x pi. And then the other term is minus I k n dot x. Okay, so that is this one. This is the vector potential, the spatial part, at least the spatial part of the vector potential in the far zone is given by this one. Okay, so that is 9.8. All right. So in this case, this integral is usually not easy to actually getting it at least in closed form. Of course, numerically you can always do that. But then get in the closed form usually is the only special cases you can do. I think maybe there's a homework problem, but I forgot anyway. Homework problem, you can integrate that in closed form. But anyway, what we'll do is to do an expansion of this one also, right? So, up to here is okay. Up to here, so this is a formula that you can use actually. That include all the before we do the long wavelength expansion and expand to multiple expansions. So this is a Barson vector potential formula. Okay, then the next step will be just use Taylor expansion of the exponential function. Okay, so it's just the rest is just depends on how not involved in the integration, and then the Taylor expansion of the exponential function is sum over Jackson use whatever use n as the index. The n is the integer. And but it's different. This is an n vector, so it need to be a little bit. And do the expansion. Is the power of this argument with n power divided by n factorial. But then this power, this quantity have two factors. So k doesn't depend on x prime, so you can pull that out. And only depends on x prime is this n vector, n unit vector dot x prime. That needs to be kept inside the integral. So outside the integral is minus I k with n power divided by n factorial. To x prime, and then you have n hat dot x prime to the n power. Okay, so that is number 9. Right? And so that's the general formula, of course. In practice, we'll just consider the lowest order, lowest n. In fact, we consider n equals 0 and n equals 1 only. Okay, so n equals 0, we'll call that, we'll see that right away. This what we call the electric dipole term. Although we are dividing it using a magnetic potential, but it turns out to be an electric dipole term. Or the n equals 0, it looks like n equals 0 is a monopole term, but then it's a magnetic field. It's related to the electric term by reducing, actually the increasing one order in the, so this is like a monopole term, but for magnetic field, but then you go into electric term becomes n equal, becomes a dipole term. And then for n equal to 1, there's two terms. N equal to 1 is there's magnetic dipole term and then electric quadrupole term. So the electric quadrupole term is of the same order as the magnetic dipole term. So again, because of the magnetic term and then the electric, the ordering is different for magnetic moment and electric moment. Okay. So we'll do that right away. But that is the general formula. I think that is the end of this. I mean, except the last section also talk about this the so-called intermediate zone. Intermediate zone means, I mean, not this one, but going back to this one, but keeping all the order. This now you're not doing any expansion. Intermediate zone is always working around you cannot use the fact that R is much bigger than lambda to simplify that, and the end result is complicated, and Jackson has a later section to talk more about that, but to summarize that in 9.11. So that gives you a transition from the near zoom to the far zoom, and it's all very complicated in the medium zoom. So we'll just ignore all that. We'll not talk about that further. So we are mostly interested in the far zoom, the radiation. Okay, so